Okay, we're back with quantification test on the light. Heat test. This is a heat lamp from a cooking to keep food warm. It's a Sylvania lamp. I have to be careful here. It says 1550 watts. Cooking unit. Sylvania. InstaHeat 236 volts. Okay? So we have to start there. So if we put 236 volts in the ohms calculator that you can find on the BioGem page of protonspintechnology.com and 1500 watts, because that's all we know, it should take 6.5 amps and the bulb should be wound to 35 ohms. Okay? Which makes sense because you've got this big ceramic socket here to take that kind of load. Don't worry about this. That was an accident. It had nothing to do with this, the burned on the rubber. Okay? So, same leads. Nothing's changed. But I decided to do a more of a quantified test. Here's the ohms when the light bulb, let me just make sure everything's hooked up relatively safe. Okay. Okay. Here's the ohms when the light bulb is cold now. 3.2. Our resonant factor of 1.6. Because what happened? The element carbon went directly to graphene in one heat cycle. Okay? In one heat cycle. Let me explain what's going on. So now here's our volts. Okay, we've quantified the ohms. Now we're going to go to amps. Okay? We're going to set the meter to amps. And we're going to set it to 20 amps DC. Okay? And we're just going to put this in line here. Over to the negative pin. And this to the positive pin. Here. Okay? In superconductivity, because I'm the person who developed this platform, I just want to mention a note. If you're an automotive builder, you get to pick the color of your wire. Okay? So, I'm an automotive guy. Purple will always be hot. Blue will always be cold. Okay? Always. In this power. So if you're on a spacecraft, or if you're an automobile, if you're home, if you're looking at an appliance, those are the colors now. Everybody got to pick theirs. Germany got to pick theirs, yellow and brown and black. America got to pick theirs, red and black and white. These are mine. Purple and blue. Just remember that. I've broke out to here so we can do multiple tests, but it's still the same size wire. Okay? So now we're at amps and ohms. Here's where the reactive power has taken place. So if we go 65 volts, because that's what it's using. This is right out of the power, out of the Hydro-Me circuit. Okay, it's Hydro-Me minus 1.0. We'll talk about that later. But the circuit goes 0.33 up click, 0.33 down click squared. That means it goes double negative, double positive, positive negative, negative positive, squared. Okay? There's the amps when the light bulb is hot at 400 degrees. I looked up light bulbs during the intermission here, the heat light bulbs, and a regular heat light bulb at 275 watts is about 140 degrees of heat to keep food hot at 140 degrees at 8 inches away. I can't find any more about that. So I did the BTU calculation, and at 1500 watts, this light bulb should be roughly about 300 degrees. Okay? Now the light bulb, when it's hot, is 2.5 ohms. Cold, it's 3.2, but hot, it's 2.5. The half resonant factor of 1.6 of graphene. Okay? So this is how it's calculated. You had 304 watts coming out of the watt load meter. But the power supply was taking up most of that to go from AC to DC. Okay? Which makes sense. The ohms from the power supply are 21 ohms because it's a safety power supply based on Ohm's law. So those two calculations, they make sense. Okay? The amps, the 26 amperes, that's why the light bulb is so hot now. Because we've been able to effectively stuff more amps in the light bulb by the reactive power. The kilowatts is now 1.7 kilowatts, which makes sense to the BTUs and heats and joules and Celsius calculation that's mind-boggling after a while that I did in the last half an hour to an hour while I pondered this to bring this back to you. But what's really happening? I'm only using 24 watts of energy. That's it. To make this light bulb 400 degrees. That's it, 21 watts. So now let's clear this calculation and let's just say that we're at 3.1 amps, 65 volts. Yeah, we don't have to clear it. That's what it is. It's 24 watts. Where I was confused is I left this open. I left the resistance open until I did the resistance calculation across the light bulb, and I got this. Yeah, actually, I got this. I pondered this for a moment until after this. 21 ohms, okay? Which makes a little bit more sense because the 21 ohms is the power supply, not the light bulb. Even at that, even at 203 watts, to take a 1500 watt light bulb that hot is very impressive, okay? That is, I deregulated myself in the last video. Now I'm quantifying myself in this video. So that's impressive. That's extremely impressive. So go back to the resistance. Even when it's cold at 3.0 equals 28 watts to fire the light bulb at 9 volts, reactive power, 1.4 kilowatts. That's very square to the light bulb, okay? That's pretty square to where we're at if we stay at that volts. But if we go to the volts that the light bulb is twisted at, it's here. I've always said this, that the incandescent light bulb is more efficient than the fluorescent light bulb. Tesla knew this. He knew that the reactive power coming back out of the motors in a power balance loop, he didn't charge for lights. That's what pissed Edison off. He charged for horsepower. Give the lights away because I want you to work 24 hours a day in the factory and not worry about the light power. Edison wanted to charge everybody for the light, but Tesla knew this. He knew the reactive power. So basically, there's nothing spooky here. It's Ohm's law and Tesla and Gibbs squared Faraday double Tesla. Okay, let's take a look. Okay. And hold on. Okay. Okay. Here we are. There's the light. There's the amps. And there's the volts. 21 watts of reactive power to fire this light bulb. That's very impressive. The power companies would be broke if you thought about that for a moment. But that's not true. Because if you had a power bill that was $100, $80 of that power bill are taxes and transmission lines because they're trying to overcome the bounce back of reactive power. Even if the solar companies are giving active power back to the grid, they're calculating it as reactive power and ripping people off. They're raising the rates on everybody right now. I was just at a Sempra meeting. I'm going to unlock it, the video right after this, and tell you that we're not going to sell the fishing pole to them. We're just going to become a power producer for you. So I make sure this power comes to you proper. Okay? We're doing it here, and we're going to show you that in a moment. Okay? But let's stay on light and heat for a moment, because this is relating to a current customer. The current customer happens to have 3 10,000-gallon water tanks that he wants to heat up. No problem. No problem. Okay? The light bulb should be nice and warm by now. Okay. Okay. What's nice is the light bulb didn't just blast on and burn out the element. It just kind of took its sweet time, which is another problem for the power company, is the demand. Once you turn something on, they really get you on demand because it hurts them in their pocket. So back to the power bill. That $80 transmission thing, maybe you, would be more than happy to even pay $40 instead of $20 for your actual use of electricity and save $60 on your power bill. But that would save the power companies because they're going broke right now. They're going broke because they can't afford, they don't understand how to control the reactive power. And I'm definitely telling them that I can, but I'm definitely not telling them how, because that's patented, it's copyrighted, and I own it. And I'm making sure for the people that this superconductive grid comes to the table, because it relates again to the photosynthesis cycle. The electromagnetic grid is blocking the photosynthesis cycle to stop the oxygen and the trees from their carbon dioxide production, and it's stopping the cyanobacteria from producing oxygen in the ocean. We need the oxygen to break open the CO2. Once the grid goes at nighttime, it bounces off the ionosphere and stops photosynthesis. Once the Earth turns, because the United States of America is at 60 hertz, perfectly matching the phase angle of the sun in the electromagnetic spectrum, the standing waves amplify at nighttime, and we directly affect the coral reef and the cyanobacteria patch, the biggest one, in that region. We're taking away their food. If we don't have fish, we don't have coral, because coral eat the defecate from the fish. If we don't have the cyanobacteria, we don't have the shrimp, krill, and lobster that the fish eat. Fine, it goes into the hydrogen state and produces oil. There's the proof, okay? It would rather do that. It doesn't care about us. It doesn't really give about human. It only does two things. It makes oxygen or oil or hydrogen. That's it. It doesn't need to break open the CO2. It just uses the graphene of the CO2 to carbonize the oil. It doesn't need it. The corals need it. They need the defecation to suck the CO2 to build the coral. It's a pretty basic chain, okay? So now the light is nice and hot. Okay, 400 plus degrees. That's a pretty nice Kelvin. It's getting hotter because this is technically the second or third heat soak. About the fourth cycle, this will probably get hotter. And there's my amps and volts. They're not going to go up. And my watts were 304. Now they're going down to 303. Okay? Because of the volt amps are going down as well. It was 319, now it's 315. Because the power supply doesn't have to work as hard, because this doesn't have to work as hard over the carbon. So the Cooper-Puckta chains are taking effect instantly in this light bulb. It happened in the heating elements. That means it's going to happen in your water heater. That means it's going to happen on your cooktop. That means it's going to happen in all your light bulbs. Now, let's go look at the fluorescent lights. Okay? First, we have to take a picture of this. That's right, boys. Okay? That's my hydride fuel thruster. Okay. One moment. I'll be right back. I just want to double check for a mental note on the numbers. I should have been more prepared. I was looking for my lux meter. You're just going to have to trust me. You see how purple the light is versus this light? The one above me is Faraday. This one's puffed up. about 120 volts. Clean wave pattern, and you have more looms off of a fluorescent bulb. But do you see that? A standing wave right inside the fluorescent light. The camera can pick it up, but your eyes can't. That's extremely healthy for you. Proper use of plasma as a motive force. Self-resonating in the light bulb. Pretty cool, huh? Nice, easy, standing waves. And see how purple the light is? That's more Kelvin. When we did the lux test, bouncing off this dirty floor, the other light was 5, this one was 19. If I had the meter handy, I would grab it. You're just gonna have to stay tuned because I'll do it later. See how they're resonating? And the first one's just kind of waiting its turn. Pretty cool, huh? There you go. Thank you for watching. This has been your update on 4-phase power superconductive grid, brought to you by Linear Pole Magnetism and Revolutions. For more information, visit www.protonspintechnology.com. Thank you and have a good day.